Welcome to this lecture. This lecture is basically based on the orbital angular momentum. Orbital angular momentum play a very important role in in quantum mechanics. So I will start with the basic definition of this what we call orbital angular momentum. Not orbital angular momentum, but I will start my topic with the with the angular momentum as we study in the classical mechanics. In classical mechanics, angular momentum is defined as L is equal to R cross P. R is the position vector and P is the momentum, linear momentum. So mathematically it can be represented as in the form of a determinant right. This is a mathematical representation of this. So it can be written as ypz minus pyz, or I can say that zpy into I cap plus zpx minus zpx, and this is xpz into j cap plus xpy minus ypx into k cap. And let me express the things in terms of corresponding components. So that means this component is known as x component, this is known as y component, and let me call it as z component, right? So this is the classical interpretation of angular momentum. Now I will talk about angular momentum, but keeping in mind quantum mechanics. So in quantum mechanics, we will talk in terms of operators. So operators play a very important role in quantum mechanics. So let us define angular momentum operator, and let me call represented by L cap, and let me call it as orbital angular momentum operator, because angular momentum is relating to the orbital motion. So that's why I'm calling it as orbital angular momentum. And as I'm talking about quantum mechanics, that's why I'm introducing its operator. So let me define its operator is R cross P. So it is, this R is a position operator and this is the momentum operator. But as I know, this R will remain as it is cross, but momentum operator is iota h cross del, right? So that means minus iota h cross r cross del. This is a one way to looking at it. But if I try to express it in terms of components, so in component form, this L operator can be written as, means it has three components, Lx, Ly and Lz. So these are represented in operator form in this way. So keeping above equations in mind as we did earlier, say if I keep these things in mind, so using all these things we can express this momentum operator as like this. means with different components. So it is the first component Lx, it is y operator, pz operator minus z operator, py operator, this is ly operator, it is z px minus x pz, and this Lz operator can be written as x py minus y and px operator. And if I substitute values of momentum, linear momentum operators, then this reduces to minus iota h cross y curly over curly x minus z curly over curly y, and this Ly can be represented as minus iota h cross z operator into curly over curly x minus x operator curly over curly z, and this can be written as minus iota h cross x curly over curly y minus y curly over curly x, right? So things can be written in this form. So these are the different components of angular momentum operator. Also, square of orbital angular momentum can be written as, that is, L square is equal to Lx square plus Ly square and Lz square, and all are operators, so these can be expressed in the operator form. Also, another very important thing which we have to keep in mind, that Lx, Ly, Lz and L square are all Hermitian, right? That's what we have to keep in mind. Then there are certain important results which we have to keep in mind. So first result is the commutator of Lx and Ly, or Ly Lz, or third thing that Lz and the Lx, right? So we have to find out their values. That so to find out these relations, let us proceed as follows. So first of all, I will consider this, and similarly we can find out all others. So let us start with this part. So Lx, Ly, its commutator. Its commutator can be written as, let us substitute their values. So if I substitute their values, so it is y pz minus z py, as we did earlier, it is z px minus x pz, right? So now what do we do? It can be simplified as, this is y pz, it's commutated with this, and right, so it is z px minus x pz, then minus z py, it's commutated with z px minus x pz, right? So it can be split into two different terms. Now what I will do, I will again expand this, so it can be expanded as y pz comma z px, its commutator, minus y pz comma x pz, then this can be written as z py comma z px and minus minus will become plus, so it is ZPY and XPZ, right? So these are the four terms which we are getting. Now we have to simplify every term separately. So first of all, I will try to simplify this term, then I will try to simplify this term, this and this term. So I will talk about it later, but its value will become 0, its value will become 0, and its value means this commutator will be equal to, this is y, p, z, z and px, and the value of this last one will be, its value will be x x commutated with z pz into py. Its value will be equal to this one. I will talk about these, that how these two will become 0 and this will be equal to this one, right? I will talk about it later. So first of all, I will try to simplify it. So it will become y pz z px plus x, sorry, not x, but it is z pz and it is py, right? So I am getting this one. So let me make it simplify. So it is y, it is iota h cross with negative sign into px plus x, it is iota h cross, it is py. So what I will do, I will take it outside, so iota h cross can be taken outside, so it is xpy minus ypx, right? And this is nothing but this is Lz. So if it is equal to Lz, so that means it can be written as iota h cross Lz. So that means, in nutshell, what I am concluding, that Lx Ly, its commutator is equal to iota h cross Lz. And similarly, I can prove that Ly Lz is equal to minus iota h cross Lx plus, and similarly Lz and Lx, its commutator, they all are operators. So if I missed cap somewhere, so you put it accordingly. So it is iota h cross Ly, right? So these are the different relations which we are getting. Now let me try to prove that this is equal to this one and this is equal to this, this is equal to this and this is equal to this. So to do this, let us proceed as follows. So yeah, so let me start with, first of all, I will start with this ypz comma zpx. Here I will use a relationship that a comma bc, if they all are operators, then I can write down it as abc plus bac, and similarly I can write down this as abc plus acb. So I will use these relations here. So let me simplify this, and this can be simplified as, it is y pz comma z px plus z ypz comma px, right? So here I use this particular relationship, and then I will use this relationship for this, for the simplification of this. So it is y pz z plus y, it is z, it is pz, and outside it, here it is a x plus z into y pz px plus y px, and it is pz, it can be taken outside. So if I try to look at it, and then pzz, it will remain as it is, but this is a 0, this is also 0, this is also 0. These are standard results. So that means, and this px is multiplied by with it, so it is y pz z, and it is px, right? So that means this term is equal to this one. And similarly, we can prove the another relations also. So let us try to go for the another term, and another term which we are considering, it is y pz comma x pz. It can be expressed as y pz comma x, its commutator, into pz plus x. Then I can write down y pz comma, it is pz. Now it can be further expanded, so if I expand it further, it can be written as y pz x plus y x, it is pz, and pz can be, this pz can be taken here, right, plus x, it is y pz, it is pz plus y pz, it is pz, right? So now its value will also be 0, its value will also be 0, its value will also be 0, and its value will also be 0. So this all makes it equal to 0. And let me talk about another quantity. So the another is basically, it is z py comma z px. It can be written as z py comma z px plus z into z px comma, sorry, it is z py and it is px, right? Now expand these, it is z py, it is z plus z z py, and this px is here, plus z, it is z py px plus z px, and it is py. This is equal to 0, this is equal to 0, this is equal to 0, and similarly this is equal to 0. So everything will comes out to be equal to 0. And the last term which I had to talk about, and the last term is basically, it is z py comma x, it is pz. Its commutator can be expressed as z py comma x, it is pz plus x, z py, not comma, comma will be here, yeah, so this way, Now what I will do, I will expand these terms again. If I expand this, then it comes out to be z py comma x plus z x. It is py, and this pz will remain as it is plus x. And now I will expand this commutator. So if I expand this, it is z py comma pz plus z pz comma py, right? So if I do this, then this will not be equal to 0. This is equal to 0, this is equal to 0, and this is equal to 0, and this x will go to here. So it can be written as x, it is z, it is pz, and it is py, right? So I have to use all these results as we see earlier. So here what I am concluding from earlier, that this Lx, Ly, Lz, they do not commute. If they do not commute, that means they cannot be measured simultaneously. So this we have to keep in mind. This is a very important thing, right? Then there are certain other relationships or certain very important commutator relations which we have to keep in mind. So let me talk about important commutator relations. Let me talk about important commutator relations. So first is xlx. Let me try to solve it. So this x comma ypz minus zpy, this is one commutator, and let me try to simplify it. So this can be simplified as this is x ypz, its commutator, minus x zpy, right? And here I will use simple formula that this a bc is equal to abc plus bac, right? So if I use this commutator relation, so this can be modified as this is x y, x, y, and pz can be taken outside, and okay, x, y, then bac. So that means this y as it is, and this x pz as it is, right? And similarly, this can also be expanded in this form. So it is xz, it is py minus zx and py, right? So this is 0, this is 0, this quantity is 0, and this quantity is 0. So everything comes out to be 0. So that means xlx is equal to 0. Now there is another relationship which we have to keep in mind. This is one very important relation, and another is xly. So if I try to find out it, then how it looks like. So it is x, it is zpx minus xpz, and this is equal to x zpx minus x xpz. Now let me try to modify it. So it is xz and it is px plus z, it is xpx minus xx, it is pz minus xx and pz, right? So this is equal to 0, this is equal to 0, and this is equal to 0, but this is not equal to 0. So xpx is equal to basically iota h cross. So that means this can be written as it is zxpx and it is z iota h cross. So if it is so that can be written as iota h cross z. So if I sum up this result, so it is xly, its commutator iota h cross z, right? So this is a very important result. Then another one is another result is basically this one. This is this x lz, its commutator. Let us have a look at it. It is xpy minus ypx, and let me expand it. So it is xpy minus x, it is ypx. So let me go to it. So it is xx, it is py plus x xpy minus x, it is y, it is px minus y, it is x, and it is px. So this is equal to 0, this is equal to 0, this is equal to 0, but this part is not equal to 0. So if it is not equal to 0, it is equal to iota h cross. So it is minus y iota h cross. So it is minus iota h cross y. So if I sum up this result, then I can xlz, it is equal to minus iota h cross y. So let me summarize all these results now. So if I summarize these results, I can express this xlx, its commutator equal to 0, xly, its commutator is equal to iota h cross lz, and this xlz, its commutator, it is equal to minus iota h cross, sorry, not z, but sorry, it's yeah, so it is basically z, right, and it is y. That's what we are getting. And similarly, if in place of these positions we are having a momentum operator, let me call it as px and lx, then it is equal to 0. It is px with respect to ly, its commutator, it is equal to iota h cross. In place of this z, we have to write down pz. And similarly, px lz, its commutator is equal to iota h cross with negative sign py. So these are a very important relationship, right? Then let us consider another commutation relation. It is x l square, its commutator, it can be written as x Lx square, Ly square, Lz square. So it is x Lx square plus x Ly square plus x Lz square. So x with Lx, this is equal to, this is x Lx commutator with Lx plus Lx x Lx, right? Similarly, this can be written as x Ly plus Ly x Ly. Similarly, this can be written as Lz, not Lz, but x Lz. It is Lz plus Lz, and it is x Lz, right? So as we know, this is equal to 0, this is equal to 0, and this is equal to iota h cross z, and this xly is also is equal to iota h cross z, and xlz is equal to minus iota h cross ly, and it is also minus iota h cross ly. So if I put their values, so then what I am getting, yeah, it is iota h cross can be taken outside. So if iota h cross can be taken outside, then here it is Lz Ly plus x, sorry, not z, but it is z Lyz, okay, Lyz, right? It is Lyz. Then it is here, it is Lylz, not Ly, but it is y, okay, sorry, yeah, it is y, and it is also y. So it is y, and it is y. So that means it is minus iota h cross, it is y Lz minus iota h cross Lz, and it is y. Sorry, iota h cross can we have taken outside, so here it is it should not be there, and this iota h cross again it should not be there. So that's what we can prove it in this manner. And similarly, if we are having pxl square, similarly I can prove that it is equal to iota h cross pzly plus ly pz minus it is pylz minus it is lz py, right? So in this way we can express it in this manner. So these are very important commutation relations. So this is all about angular momentum. Now in the next lecture I will generalize this formalism of angular momentum, whether it is a spin angular momentum or orbital angular momentum. So we will use a general notation in place of L by J. So I will talk about that in the next lecture. So thanks for watching this video.